This is a review video of electrostatics. In this unit, we talk about what is charge, how we produce charge, and with the existence of a charge, there's a lot of things can happen. Interesting like physics quantities or interesting physics phenomena would happen with the existence of charge. And a few physics quantities we talked about include electric force, electric field, electric potential energy, and electric potential. And they have their abbreviation looks like this, and this is their unit. So in charge, we know charge has positive charge and negative charge. And in this case, for example, there's a positive charge exists in the universe. This charge will naturally create an electric field around it. And if it is positive, the electric field line will go outward. But if it's a negative charge, the electric field line will go toward. So this outward, outward or inward, this kind of direction is just like a convention that we like all physics or all scientists agree upon. So this is a convention. It's always starting from the positive and at the negative charge. And there are a few ways to create charges. If it's insulator, we can create it by friction. We can just do this. We can do this, and then kick out some electrons. Or we can do it by induction, and we will talk about an example about induction later. But anyhow, once we create a charged particle or like a charged object, this charged object will create an electric field. And as long as if there's any other particles coming into this system, into this field, he will feel influenced by this source charge particle. Therefore, between them, they will create an electric force. If it's positive, it will be it will be repulsion. If it's negative and positive, it will get you'll get attraction. So with the existence of another particle, we will get a force between them. Now I can take this charged particle and move it inside, outside. I can move it around. And with the electric force, and if we move this one around, then we will get a displacement. And since we know force times the displacement, it will give you the work. So which is the potential energy here. So now we can see the force is connected to the potential energy through the work energy theorem. And through the definition of work, I should put it this way. And then similarly, since there is a potential energy, for example, if there's a mountain, we know a particle on the top of mountain, it has higher potential energy. If it's lower, it has a lower potential energy. But actually, the landscape, like the elevation of the mountain, does not really, it's always there, no matter you have this extra particle there or not. If there's no particle there, I can still define, oh, this is high elevation, this is low elevation. And that elevation in the language of electrostatic, we call it potential. So this is like a potential, it's like the elevation. When you put a particle on it, this particle will gain the potential energy. That is the potential energy here. So it is very important to have a nice, vivid imagination of these four physics quantities. And so now I'm gonna just write down its relation from my intuition. So we know any source charge will create an electric field. And when a test charge coming, or like other charges coming into this field, this charge feels a field, and they will create a force between them. And if I push this particle, this particle, a certain amount of distance, then I will get the potential difference. It will do some work, which is the potential difference, which is the force times the delta x, where the force is QE, and the displacement. This is a relation between them. And same thing here. V is the elevation. And when you put a charge at the elevation, this charge will gain an electric potential energy. Put a charge next to the elevation, you will get PE. So you can see it's somewhat symmetric, so we can reasonably think about it in this way. If we have an electric field at some certain point, and then if we move this one from here to here, we can also define an E times delta X corresponding to, right now it does not work because there's no any extra charge. It's just the elevation and the field. So we can similarly find a relation that V equals to E times delta X. Okay, so this is just a generic relation between these four, but how to use that will take some practice, and that's what we are going to do in the following 3 examples. This example is about charge distribution. Charge distribution is actually relies on the concept of equal potential. So we know that if there's a potential difference, and happens like there's a potential difference like a mountain, then when you put a ball on higher potential, it will naturally want to roll down to lower potential. And charge distribution is really rely on that idea. So when I say that, I mean, for example, if you look at this case, if I know now I have a conducting ball which carries a charge positive Q, then the most likely the charge distribution should be evenly distributed. And the reason why it wants to be evenly distributed instead of all distributed on one side instead of another is because of the equal potential. The charges, they were distributed in a way that they will maintain that every point in this conducting ball has the same potential. If there's any point or any part in this conducting ball has a different potential, then the charge will want to move to lower potential or higher, move from higher potential to lower potential. The charge will want to move around. So eventually, when it comes to equilibrium, all these points will be evenly distributed on the surface because they wanna make sure the potential on every point on the surface is the same. And so that is the core concept. Now let's look at this case. In this case, this one is more sharp, this one is more less sharp. So what you will see is most charges will accumulated at the pointing place. Some charges here and very little charge on the side. But there's a lot of charges here. And again, this distribution coming from because these charges want to maintain the equal potential, the same potential on the, in this egg. On this egg, they want to maintain the same voltage. And because they want to maintain the same voltage, so the charge density will be different depending on the shape of this object. So here's another question here. If I have 2 identical conducting ball, one is charged, one is uncharged, then I bring them together with into contact, and then separate them. Then what's the charge distribution in the end? So say this was charged with Q. When I bring it into contact, This has 4 charges, this has no charges. But since they're in contact, this guy has 4 charges. Apparently this one has higher potential, this one has no charge, there's no potential. And since this is higher potential, this is lower potential, so all the charges want to flow from high potential to low potential. So eventually, this charge will be evenly distributed on both conducting balls because they're identical. So here this one will carry charge Q over 2, this one will carry charge Q over 2, and when you separate them, this one will naturally carry a charge Q over 2 and a Q over 2. So now these two will create a repulsive force between them. The same idea here. This one is positively charged, so it has a lot of higher potential. This one is negatively charged, it has lower potential. When you bring them together, all the positive and negative, they will start to flow from high potential to low potential. And then eventually, because this is positive Q, this is negative Q, and charge cannot disappear, so positive Q plus negative Q, totally these two together will have no charge at all. Because it's not like they completely have no charge, but it's just like the net charge is 0 on both sides, because part of the positive charge goes here, part of the negative charge goes here, and they balance out eventually. And you can see it is indeed equal potential, like the potential is the same in this structure. So when you separate them, this one carries no charge, this one carries no charge. All right, the same idea here. This one carries 3 charges, 3 Q. This one carries no charge. But this one is, its radius is twice longer than this one. And when I bring them into contact, you can imagine this charge will start to redistribute it. And what's the final charge on this one and on this one? So in this case, we need to give it more thought. The whole point is what's happening here and how they redistribute the charge to make the equal potential. So this one, we know totally Q1 plus Q2, the net charge is 3Q. So totally we have this 3Q to redistribute it, right? So totally it's 3Q. And then if we look at the potential here, this potential is V1. Potential of the ball is V equals to KQ divided by R. At this point, since the potential is the same, so the larger R will carry larger Q. So we know that because this one has its radius of twice larger than this one, so Q1 compared to Q2, it should be like 1 to 2, or we can say Q1 to Q2, it should be 2 to 1 because Q1 is larger, sorry. So which means the charge on this ball should be twice the amount of the charge on the second ball. So if we combine this information and this information, we can reasonably figure out that Q1 would be 2 and the Q2 would be 1. So if I have a 3Q here brought into contact and it is brought into contact with another little ball, then eventually you will have 2Q on this ball and only 1Q on this ball. But if you look at the density, you will find this one is more dense. Alright. So now this is just one example talking about like how electric force, field, potential energy, how they are connected, and in a point charge example. If there's only like some point charge, here, here, and here. Now let's draw the free body diagram for the electric field at P. So P at this point, I haven't put on any charge yet, so there's no charge. I just wonder what's the field for this P. Because we know this one will send out a field like this. This one has a field like this. This one has a field outward. And when this, so whatever in the middle in the intersection, like all this field line will kind of like aligned or like redistributed because they also feel the source from the other charges. So the question is, considering these three charge sources, what's the free body diagram for this, for the electric field on this? So let's see. The first, it will feel an electric force from here, which is going downward. And then it will also feel an electric force from this. It's this way, right? And then you will also feel electric force from this point, which is pointing outward. So I'll say this is E1, this is E2, this is E3. And of course, if I give you a charge here, you can plot the same free body diagram, but for the electric force, and you will pretty much just do the same thing. You just need to be careful about the directional force. But now, since you have done similar question in the expert TA, so here I just wanna draw the free body diagram for electric field instead of force here. But the logic is the same. And then the second question, write down the electric field for from like individual charges. So for example, E1. This electric field of a point source, this is E1, is KQ divided by R squared. Here the R is 3. And the direction is going down. Alright, so that covers the first one. E2 is the electric field between these two. So we have KQ over the distance between these two. If this is 3, this is 4, then this would be 3, 4, and say this is R equals to 3 squared plus 4 squared, take the square root, which is 5. So this distance is 5. And what's the direction? Let's see. Point inward. Point inward with the angle theta. And this theta, let me try to define it here. This theta is arctangent 3/4. Okay. And the E3 is the electric field from this. So the electric field of this point from this source is KQ over R squared. So these are the individual electric field. Now this point, it feels the field from this. So totally, we wonder what's the net field. What's the net electric field? And we know this net electric field, it's a two-dimensional problem, so we cannot just say, oh, it's E1 plus E2 plus E3. It doesn't work that way because they are all in a different direction. So one thing we can do is we can separate out the X direction and the Y direction. And then we can sum up the component, all the X component of each of this individual electric field. So the net electric field, the x component, so let's see. First, E1 is completely in y direction. It does not contribute to the x component, the x component of net force at all. So this one doesn't work, doesn't do anything. But this one is partially on the x direction, also partially on y direction. It's not really on, any of them, completely on any of them. So let's see. This one, E2, it has the, what's its x component? This is a good time to review your trigonometry. So this is E2. E2 has an x component and a y component. So if we draw a triangle here, you can see E2 times cosine theta will give you the x component. And here this is the y component, which is E2 times sine theta. So now let's fill this in. E1 doesn't contribute to x component, but E2 has E2 times cosine theta. And E3 is completely on x component, so it definitely contributes to the net force, x component of a net force, which is negative because it's going in that direction. All right, so now we can put things together. E2 is KQ over 5 square cosine theta. And so here you can put in the calculators, and the calculator will give you an angle, and you can use this angle to find cosine theta or sine theta. So if you do that, cosine theta, you'll find it would be it's like 0.8. And E3 is KQ over 4 square. So if I figure out this math, simplify this, I will get KQ, because both of them has a KQ, times 0.8 divided by 25 and minus this. So I'll come back to this number. In y direction, E net y, this one. So let's see what contribute to this component. In y direction, we have E1 completely on the y component, on the y direction. I put a negative sign here to indicate the direction. And then E2 has also like a partial contribute to the y component, so it will be E2 sine theta. And E3 has nothing to do with the y component, so we don't care about that. Now E1 is KQ over 3 square plus KQ over 4 square times sine theta. So sine theta is 0.6. And then you can simplify this with the number and a KQ. I'm gonna leave this. If you work out the math, put in everything in the calculator, you will get x component of net electric field looks like this, and the y component is this. If I want to draw this out, you can see this is the x component, this is the y component. So since x component, y component, and so which means my net electric field is the vector pointing in this way with this amount of magnitude. So now let's find the magnitude and the angle for this. This magnitude, we can put this one here. There's a little triangle, so it's nothing but EX squared plus EY squared. then square root of that. So please go ahead and finish this by yourself. And again, we always talk about this to indicate a vector, we need at least two information. So in this kind of scenario, we have magnitude, we also need the angle to suggest the direction. So conventionally, because this is a coordinate, conventionally people talk about the angle, they mean this angle. But you can also say this angle but with a minus sign. But conventionally we say counterclockwise is positive. So how do we find out the angle? So we know this is 180 degrees, so we kind of need to just figure out this out first and then add up 180. So this angle, let me call it phi. We know the tangent phi is EY over EX. Okay, so think about it by yourself. This is tangent. And since it's EY over EX, EY is 0.77 KQ. X is 0.3 KQ. So it's 3 over 7. So the phi is arctangent. So this is the magnitude and this is the angle. This is the angle for this. And we need to add 180 degrees. It's just like the way like conventionally people say the angle, they mean this one. So the actual, I'm gonna name this a little bit differently. Phi. This is phi naught and this is phi. Alright, so this is the idea. Now if we put a negative charge at this position P, what's the net force on that charge? So let's see. This part, if now I put a negative charge, this negative charge has attraction here, has attraction here, has repulsion here. But totally, what would happen to this charge? Will it be attracted or will it be repelled? So let's find out. Here we draw the electric field. This is a total influence from all this source particle. And this is the net electric field. So this, the sum of these three is equivalent to this one. So this is net electric field, which is moving in this way. Now what's the force on it? The net force is the charge, is whatever the charge I put in, feels the force, feels the field from the other charges. And again, this one has an x component and a y component because E is a vector in two-dimensional. So what we can do is we can write down the x direction. This net force in x direction is a minus q times this one. It's a minus q times the electric field in x component of electric field. So we have minus q times this. So which is this. And we can do the same thing for y direction, where the net force in y component is also the same, but the component right now is this for y. So totally, if you do the math, you'll get this. This is the net force, x component and y component. So now let's see, will the charge be pulled in or pushed away? If we draw the free body diagram for here, if we draw the free body diagram or like the picture of this net force, for this charge, it feels a force and the x component is positive and the y component is also positive. It's actually more positive. So x component, y component, so the net force will be pointing in this way. And what it means is, if I put a negative charge on this P, it will feel a net force pulling in, like pushing in this direction. So it seems like these three charges, the net effect of these three charges, eventually they determined to pull this inward, like into, you know, like their little group. So this is pulling. Okay. So when you do this problem, try to imagine this and think about it. Make a very nice picture in your head. So this question is saying, what's the potential energy at minus Q charge at P? All right, now this guy, we know this one wanna be pulled in, but what's its elevation? Like, what's its potential energy? And again, the total potential energy at this point, because potential is a scalar, so this potential will, the potential at this point is nothing but, the total potential here is nothing but the summation of all the potential between this one, and this one. Okay. So the potential between these two, potential energy between these two will be K plus Q. Here is negative charge, so it's a minus Q, divided by R, and the R is 3. Same for this two. This one will also provide a potential, that is K, Q minus Q, that's Q, divided by this R, which is 5. And also this two. This one will feel the potential energy because of this one as well. So it will be K plus Q minus Q divided by 4. So go ahead and simplify this, and you will get you'll get like negative 1/3 plus square. So go ahead and put this number in the calculator. You should get some numbers there. Okay, so this is the potential energy, and here you may notice a difference. When I use KQQ over R squared, KQ over R squared, KQ over R, like any of them, you may wonder, sometimes when I calculate potential energy, I always keep positive sign, negative sign. I'm careful about this. But I don't really do so when I calculate electric field or electric force. For example, this one, it is the E2, this one is negative, but I still only take its positive value and only indicate this direction. And there are many ways to do this, and the way I choose to do this in this way is not because KQQ over R squared, not because this one is wrong. It's not because this is wrong, this is completely correct. But it's just when it comes to the vector, I like to be very careful about the numbers and the magnitude. So here, what I always do is I only calculate the magnitude. Magnitude is always positive, so I will ignore all the positive and negative sign here. I always calculate the magnitude and then judge the direction by myself, like from my physics intuition. Like if it's attractive, if it's repulsive. In electric field, I will judge whether the electric field should go outward, inward. So I will judge it from my physics intuition and keep the magnitude always positive. However, I don't need to do so for potential, because potential, there's no, it's not a vector, so I don't need to care about the direction. I can just add them up. So when I add them up, whether it's positive or negative becomes very important. Yeah, so the sign will become very important, and it's not that trivial to judge the sign from intuition, so I kind of just leave it as it is, like leave all the sign in, and that will help me to think about this. It will just naturally give me the correct sign. Okay, so if that makes sense, we'll go ahead and think about this problem. What's the potential at P? Potential at P is asking, now we know if I put a particle here minus Q, this guy will feel a potential energy. But what's the potential, what's the elevation at that level if there's no charge? So we can think about this. Potential energy happens when a charge is put at that potential. Now I know my potential energy, it is this. And the charge that I put on, it was minus Q. And what's the V? I can just easily figure that out by dividing minus Q on both sides. Okay, so this would be your answer. Please go ahead and simplify that by yourself. So I hope in this example you can clearly see the structure is pretty similar to what you learned in mechanics. The only thing you need to pay attention is how to do the vector addition, and how is that vector addition different from scalar addition, and try to be careful about the sign, the direction, the magnitude, and all of that. This is another example about a parallel plate. I charge the parallel plate. Say if I have a charged parallel plate, like two of them, one has 5 coulomb on it, another one has negative 5 coulomb on it. And so when you put them together, from the demonstration, we know between these two will create a uniform electric field. And this uniform electric field will point it from positive to negative. So it would look like this way. And the question here, one good question here is what's the potential difference between P and Q? Okay, so I would like to explore about like how like some of you or like most people would approach this problem. The first thought is about, hey, why don't we just calculate potential at this point and calculate potential at this point and then subtract them? So if you want to do that, that's totally fine, but we need to figure out what's the potential at this point. So what's the potential at this point? The potential at this point, you may this may remind you like, oh, potential is just KQ over R. All right, the problem is, what is the Q that we are using here? Are we using this Q? Are we using this Q? And how about R? Is this the R or is this the R? So let's say this is the formula for point charge. So for example, a charge here at this point charge will provide a potential at this point. So this provides potential which is KQ, and the Q is the charge at this point of this specific charge with the distance R. However, we could have another charge here, and this charge, let's say this electrons, it will also provide a potential at this P point with the R, which is like this. So you can see I could have different charges across this plate, and the same here, and all of them have different R. That carries different R. So if you want to go in this way, one way is you can calculate the KQ over R. For each of this point, and since it's continuous, you can just integrate over this plate and integrate over this plate, then add them up because it's scalar, so you can just integrate it, sum them up. So if you want to do this, you need to do some you need to know some calculus. So go ahead and try this. But if you don't know how to do calculus, or we can use another approach or another way to see this problem. And so that problem, the way to see that problem is we can start from here. We know that electric field in this kind of geometry, it is uniform distributed. So all the electric field in this space, they are all 3 Newton per coulomb and going downward. And we know that V and the electric field, they are related in a way that if we push something along the electric field line for a certain amount of displacement, I will put in some work, or let's put in some potential in this case. I'll put in some potential. And so we can try to use this one to think about this problem. So, so this is try 1 and try 2. And the try 2, I want to use this idea. So instead of calculating this potential and this potential, I want to just calculate the potential difference between them together. And this potential difference will tell me that this E field times the delta X. E, we know it is 3. But the question is, what is the delta X in this case? Naively, you may think, oh, delta X is just this distance, which is, let me just call this distance R, okay? And distance R can be figured out by these 3 variables, but I'm going to just call it R for simplicity. So you may think it's 3 times R. But this is not really true, because look at the direction of electric field, it's going downward. You know, like not all of the electric field are trying to push the point from here to here. This electric field only provide partial effort to push the particle from here, because this displacement and electric field are not completely aligned. Alright, so this idea is very important and sometimes may be very confusing, so I'm gonna talk a little bit more about this concept in this area, but if you think you know, you can skip it. So now let's consider a bit more different situation to clarify this idea. So say here, I consider a point R and I consider a point S here. Situation 1. What's the potential difference if we push the particle from the test charge from P to S? the potential difference, because you can see this electric field is completely aligned with, is completely doing the work to, you know, push a test charge from P to S. So electric field will do all the work. So the distance here is this distance, which is R2 minus R1. And this is probably you're okay with. So in situation 2, if I want to push P to R, what happened? If I want to push P to R. If I want to push P to R, now this is a little bit weird. Because the potential, if we want to follow this rule and think about our potential difference is E times the distance between them, which is R3. But this cannot be true, because the electric field, what it does is it's trying to push the test charge downward, while this charge is actually moving, the test charge is actually moving in this way. So electric field has nothing to do with this displacement. It's completely not making any work at all, trying to push this in that direction, that perpendicular. So actually, this is not true. The potential difference, the potential, electric potential coming from the electric field is 0, because it's not really doing any work. Therefore, like no potential. And you can kind of see this fact from the equipotential line, because we know that equipotential line of this will look like this, right? So if this is a P, this is a Q, they're really on the same equipotential line. Remember the amount of energy analogy? This is P, this is Q, and this is S, this is R. So they're really on the same potential. These two are really on the same potential. So when you push, electric field does not really do anything to push it from here to here. Similar idea in the gravitation. You can see the gravitational force has nothing to do if you want to push a ball from here to here. Gravitational force only help to move this guy downward to this point when they have a gravitational potential difference. So when we want to use this one, we need to remember, this is, if you can recall, if you can remember, this is a dot product. So it's really the effective force that, the effective force contributed on this, displacement will actually make a potential difference. Okay, so then you may wonder, oh, how do I find the effective force? There's some way to do it. One is you can take this, find its effective component, effective field component on this path, and use that component to times the displacement. Or another way is you can just move particles around. So for example, to find a potential difference between P and Q, I can first move P to S. And we know if I move from P to S, I will acquire a potential this. And now I can move from S to Q, which caused no potential. It does not cause any potential change. So this, I can say, oh, I am moving from Q to S, and then moving it from S to P, and moving from S to P, we know it is, this is moving from Q to S, which is 0, moving from P to S, which is E times R2 minus R1, and it should be negative in this case. Yeah, it should be negative. And how do I know about this is positive or negative? And again, you need to, the best way to judge the positive and negative side is rely on your physics intuition. VQ and the VP, which one has higher potential? this one. If I put a positive test charge here, it will naturally, it will want to be repelled downward. So this one has a higher potential, this one has a lower potential, because everyone wants to flow to lower potential. Okay, and therefore I know this is lower potential, this is higher potential. So if I take lower minus higher, it will give me a negative sign. So this is the thought process to see this problem. There are many different ways to think about it. So feel free to explore your own way, and yeah, just find whichever way that makes the most sense to you. In this problem, what's a potential energy difference to move a charged calcium from P to Q? So calcium, this is ion which carries the positive 2 electron charge. So it's 2 times 1.6 times 10 to the negative 19 coulomb. And to move a calcium from P to Q, again, potential energy is, I can just put calcium here, and this calcium, the charge of this calcium will naturally feel the potential difference when it moves from one to another. This potential difference is VQ minus VP. That's what we have here. Okay, so now you can put in all the numbers. 3 times 2 times this guy. And of course, if I like it, E is 3, so you can put 3 inside. R2, R1 are not given, but if I give you a number, you can put in a number, then you will get a number with the unit of joule. I hope these examples are helpful, and go ahead and practice some more similar examples. And when you practice that, I would encourage you actually practice a variety of different problems. That will give you some. They will challenge your thoughts and help you to build a strong physics intuition.